If a right triangle has one leg with a fixed length of 120 centimeters and the length of the other leg is decreasing at the rate of 15 centimeters per hour, at the instant its length is 90 centimeters, find the rate at which the A, length of the hypotenuse changes, B, angle opposite the fixed length changes, and C, area of the triangle changes. Let's start by writing down the information we are given here. For a triangle, it's often best to draw a picture for it. So we have a right triangle. The length of one leg is a fixed constant. We will want to label the picture then with the constant. 120 centimeters, I will pick that leg to be 120 centimeters. The other leg has a length that is changing, it's decreasing with time. So we will want to label it as a variable, say x, and we have the rate x prime or dx dt as decreasing, therefore it's negative 15 in units of length for x over time, centimeters over hours. We're also given its length is 90 centimeters. For part A, we want to find the rate at which the length of the hypotenuse changes. Let's give the hypotenuse a name, say y. We have the rate at which x changes. We want to find the rate at which y changes. We will need to first find how y is related to x. Well, y is the length of the hypotenuse, and x is the length of one of the legs. For a right triangle, they're related by the Pythagorean theorem. Hypotenuse squared equals one leg squared plus the other leg squared. There's our related variables equation. We can now find the related rates equation by taking the time derivative of both sides. I will indicate this by a prime on both sides. When we take the time derivative, every variable is implicit with time, so every variable will get a prime due to the chain rule. On the left side, we start with the power rule, bring the power down, subtract 1 from it, but then we multiply by the derivative of the inside. There's the prime for the y. On the right side, the first term is power rule, bring the power down, subtract 1 from it, then multiply by the derivative of the inside. There's the prime for the x. The second term is a constant, and the derivative of a constant is 0. We can now divide both sides by 2 and cancel the 2's out. We want to solve for y prime here. We need to plug numbers in. We have an x, we have an x prime, but we do not have a y to plug in just yet. However, we do have an x, and as we know, x and y are related to each other, so if you have one, you will have the other. We need to plug x into there first. Let's work that out down here. So y squared, which equals to x squared plus 120 squared, will equal x being a 90 squared plus 120 squared. 90 squared is 9 squared, which is 81, and then the square and the 0 makes 2 zeros. 120 squared is 12 squared, which is 144, and then the square and the 0 makes 2 zeros. These can now be added together, and they add together to become 22,500. Y will be the square root of this. It can be plus or minus, but since it's a length, we only want the positive square root. 225 is a perfect square. It's a 15, and the square root of 2 zeros is a single 0, or the square root of 100 is 10 is another way to look at that. So this comes out to 150, and it will have units of length, which in this problem are centimeters. We now have a y that can plug in back up here, so we have 150 y prime equals the x given to us as a 90 times the x prime, which is a negative 15. So y prime, if we solve for it, will be 90 times negative 15 over 150. Now, instead of multiplying 90 times the negative 15, we can reduce the numbers by cancellation with the denominator. Everything's multiplied in the numerator, so that 15 in the numerator can cancel with the 150 in the denominator, leaving 10. It will leave a negative 1 in the parentheses, but 90 divided by 10 is a 9. times that -1, -9. So y prime, or dy dt, equals to -9. It'll have units of the length of y, centimeters here, over time, hours here. For part B, we want to find the rate at which the angle opposite the fixed length changes. On our picture, the fixed length is 120 centimeters. The angle opposite is this angle here. I'll label it as theta. We want to find how that changes. So we need to relate that theta to one of the variables that is changing, either x or y or both of them. It's usually relating it to just one of them to keep it simple. So we're going to make use of the side that's a constant, 120, and then we can relate it to either x or y, since we have the rate of how each of those changes. For example, we can use the sine function, sine of theta equals opposite, which is 120, over hypotenuse, which is y. There's the related variables equation. We can find the related rates equation by taking the time derivative of both sides, indicated by a prime on both sides. Now, before we take the derivative of the right side, we will want to rewrite it. Since it's a constant in the numerator, we can bring the denominator up as a negative exponent, y to the -1, so that we can see how to take the derivative. It will actually be a power rule. On the left side, the derivative of sine is cosine of theta, and then multiplied by the derivative of the inside to complete the chain rule. We always get a prime on every variable. On the right side, it's a power rule. Bring the power down, so I give us -120y. Subtract 1 from the power to the -2. And then you multiply by the derivative of the inside, which will give us a y prime. We get a prime on every variable when we take an implicit derivative with respect to time. So we have cosine of theta, theta prime, equals -120. We can move that y to the -2 to the denominator. That'll be y to the +2, but the y prime stays in the numerator. We can now plug some numbers in. One thing we want is the cosine of theta. Well, if we look at our triangle, the cosine of theta is the adjacent side, which is x, and we have a number for that. That's 90. And then it's over the hypotenuse, which is y, which we have a number for that. That's 150. So it'll be 90 over 150. We have theta prime, that's what we're trying to find, equals to -120. Now y prime we have found, and it's a -9, that's in part A. And all this is over y, which we also found to be 150, and then squared. We want to solve for theta prime here. We can start by canceling some things out on the left and right side. They have to be in the same position when you cancel left to right. So the 150 in the denominator on the left can cancel with one of the 150s in the denominator on the right. There's two of them because of the square. Also, we can cancel the 90 down on the left with the 9 on the right, leaving a 1 with the negative, and leaving a 10 over here. That helps reduce the numbers down a little bit. As a matter of fact, we can even cancel the 10 here out with the 120 here, and that'll leave a 12. So we have a -12 times a -1, which is just a 12. So theta prime will equal a 12 over the 150. This can reduce a little bit further because each of those is divisible by a 3 at the very least, so that will divide to be a 4 over a 50, and each of those is divisible by a 2, so that will reduce down to a 2 over a 25. It doesn't reduce any further, so therefore our theta prime, or d theta dt, is 2 over 25. The rate here, 2 over 25, will have units of theta, which is measured in radians, over time, which in this problem is measured in hours, so radians per hour. It's a positive number, so apparently the angle is actually increasing as this change is taking place. So theta prime came out to a positive number. For part C, we want to find the rate at which the area of the triangle changes. The area of the triangle has a related variables equation of 1/2 base times height. The base and height are the legs. They're orthogonal to each other. In our picture, our base is an x, so we have 1/2 times x, and then our height is 120. Now the 1/2 and the 120 can multiply each other. 1/2 of 120 is 60, so the area is equal to 60x. And there's our related variables equation. To find the related rates, we can take the time derivative of both sides. So we have the prime of the left and the prime of the right, indicating the time derivative on each side. On the left side, the derivative of a is 1, but then times a prime because it's implicit on time. And on the right, the derivative of a constant times x is the constant, but again, times x prime. Everything is implicit with time, and every variable will get a prime in its derivative. There's our related rates equation. We can now plug our numbers in. We have x prime as a -15. So now we just need to multiply 60 times -15. That comes out to -900. So our a prime, or dA dt, will be -900. Units of area. Area is length squared. We're in centimeters here. And then per time, which is in hours. So centimeters squared per hour. It's negative, indicating that the area is actually decreasing.